Welcome to part 2 of the standard model.
Actually, it's more like part 4.
Okay, well, part N of the standard model. So we've talked about leptons and fermions, which are essentially quarks. So far, just a quick summary. You have positive and negatively charged quarks, and they tend to exist in little couplet families. They all have, apparently, some sort of value that is conserved among them. Call them strangeness, charmness, bottomness, and topness. Scientists are very creative. And then there are leptons, which are essentially electrons and its heavier cousins, paired with neutrinos and their heavier cousins. And they always exist in pairs with their families. And in any reaction, the total sum of the lepton number or the strangeness or whatever is always conserved, just like color charge and just like electric charge. So now we're going to talk. You want me to talk about wave functions? What do you think? No, I'm going to talk about how photons work.
Wait, Jack, are you going to explain those on the side?
Yeah, I'm going to get to that. So now I'm going to explain what these are. They're called bosons, in that they carry the charge, and it's defined by Bose-Einstein statistics. So I'm going to just do a little bit of the basics first before I get into them. So electrons interact with other electrons through what fundamental force? Anyone? Nathan? What force do electrons interact with? Electromagnetic force. And what scientists found was generally you have two electrons. Let me get a better marker. You have, oh gosh. You have two electrons, and they're both approaching each other. They'll tend to look like that, right? And if they're smoke moving forwards, that's how they'll interact. They'll kind of rebound off each other in a curved state. And someone figured that, hey, we're changing the momentum of these two individual particles. Something has to be carried between them. There's some information that's being transferred. And what actually happens is, with Maxwell's equations, he realized that, and later Einstein proved this, that light propagates as an interacting electric and magnetic field. They kind of alternate. And what Feynman and a bunch of other scientists realized at the beginning of the 20th century is that there are photons that are, there we go, that's the letter I was looking for. There are photons that are transferred between those electrons. And there are an infinite number of photons being exchanged between these two electrons as they interact with each other in infinitely small units of time, which gives us a really smooth curve. That's hard to do math on. And there are all of these mathematicians early in the 20th century trying to derive out the system of equations, try to get to solve, knowing that photons can only travel at the speed of light, so there's some delay, and all of this madness. And Richard Feynman came in and was like, guys, it doesn't have to be this complicated. And then he took two electrons, and knowing physically what happens, says they're going to come in and then rebound as a photon is exchanged between them. And this photon carries energy and carries the force of that interaction for a brief amount of time. And those of you who want to start looking at Feynman diagrams, it does get pretty cool because you just start adding on more and more and more layers. So there'd be more and more photon interactions, so you'd add two more, then two more, then two more, until eventually you get so many that you have the infinite exchange, and then you get the smooth curve. Well, essentially, this is what it looks like when particles will interact. And when Other particles will come in. Let's say we're going to have, let's say we're going to have a proton, or a neutron decay into a proton. So we're going to have an up quark, a down quark, and a down quark. So that makes up a neutron. And all three are going to be going one way, and then they're going to rebound and go another way. And we'll have, what's going to happen is that an electron and an anti-electron neutrino are emitted, and you end up getting an up, a down, and another up. So there's some interaction that happens there, and then visibly from some other point, there's a particle that is emitted that then turns into this electron to anti-electron. And then scientists are like, what? That doesn't make sense. That should happen at the source of the reaction. There must be some other particle we don't understand that's navigating that transfer of mass and energy to some other point that then turns into what we can observe. So scientists reasoned that if there is some carrying particle for the electromagnetic interaction, that is the photon, then for other interactions there should also be some other carrying particle. So they determined that that will decay and turn into one particle, and then that itself will turn into the electron and anti-electron neutrino. Up to this point, they knew of the electromagnetic force, the nuclear strong force, and the force of gravity. Three fundamental forces. Now, how many forces do we know there are now? Four. What is that fourth force they discovered?
Weak force.
The nuclear weak force. It doesn't interact much, but when it does, it makes stuff break apart and decay. And the weird thing is, with weak interactions, one, it completely ignores all of these conservation numbers when stuff is turning into the carrying charge for that, which I'll cover in just a moment. But like lepton number and fermion number with strangeness and charm, it just ignores that. It'll go from one to the other. And looking at our universe, there is no reason for the force to exist at all. As far as we understand, it shouldn't exist. There's no necessity for weak force, which is weird. If you guys want to look more into that, feel free to. But that's beyond the scope of our lecture today. What scientists figured out is that there are particles mediating the force of all of the other ones. So they called those bosons, and they have a massive W plus and minus. You could have a plus or minus W, and a Z naught. And generally those will just kind of be emitted by some particle, and it'll go up, and it'll turn into, I don't know, use that. And that'll emit one of those bosons, and then that will turn into more particles. So going forward through time and laterally through space, that's generally what will happen. Ignore that. I just kind of made up hadrons because I don't actually know what this interaction would be. But the basic idea is that there is some virtual particle that exists for a very brief amount of time that mediates that force. And with a neutron, it's the weak force that mediates that. And with particles, you bring them close together and then stuff decays. And that's kind of how that will work. But here's the basic idea behind this. I'm going to wipe all of this. Does anyone remember on Friday we were talking about the uncertainty principle? And there's two different uncertainty principles accounting for error in the laws of physics. Can someone tell me what one of them is? Has to do with momentum.
Wait, you want just like the basic?
Just the basic uncertainty principle.
Okay, like when you know an object's speed, you can't know its direction.
Right. Your error in speed and your error in position have to be above a certain quantity called h bar. This is h bar is what's his face's Planck's constant divided by 4 pi, I think. Yeah, it's divided by 4 pi. So all it is the same thing, just smaller for different types of interactions. What's the second one? This is saying that we can't know intrinsically with the particles, something I'll talk about in a moment. Their velocity and position can't both be known within some margin of error. So can someone tell me what the second one is? You had your hand raised, Rashid?
I guess like if it's smaller than h bar, then you can know them both. Or like, well, no, so like if the object is really big, then you can know its speed and position.
Right, because if you have a lot of particles, or if you have one really massive particle, you can. Generally, that comes from if you have a lot of different particles acting randomly, they tend to, as a set, to work in one classical motion, as opposed to an intrinsically random motion. But what's the other uncertainty principle? Nathan knows this.
Go, Nathan.
I probably can't remember the.
Well, it has to do with energy and time. And it says that for any particle, its energy can change, like it can suddenly have different energy, or what that means, different mass or charge or something like that. As long as the time that that energy is changed is below, I think also h bar. No? It's below some constant that I don't know. Let's call it k.
Oh no, I just said it.
And what this means is kind of like what Mr. Atman said on Friday. I'm just going to rephrase it. You have your up quark, and it has positive charge, and it has a very small mass, and it's just going along. And then suddenly the universe is like, you know what? Let's mess with you, and turns it into a top quark. For a very brief amount of time, it has a mass in the billions range larger than, maybe just the millions range, the tens of millions range larger than what it had before. And in your body all the time, that's actually happening. You have these up quarks just changing into top quarks and then changing back very briefly. Because it's a huge change in energy, you have to have a small change in the duration of that. And just as this little side note, what do you think would happen if all of the up quarks making up the protons and neutrons in your body changed to top quarks at the same time, even if very briefly? It'd be pretty literally massive effect. And you probably wouldn't exist very long because the force of gravity, even for that short amount of time, would be in the order of magnitude of like 10 to the 7 or 8 times larger. And your body couldn't sustain that. So after a certain amount of time, it will just turn back into your regular old up quark. So there's this idea of spontaneous existence of particles. So particles can change, or in empty space that has just free energy, there can, for no reason at all, be particles that spring into existence. So let's say an electron and a positron, so anti-electron, and then they'll clash and emit light, or in the case of a photon, and so you'll have all this spontaneous generation of particles. Well, a cool thing is with an electron, it's technically constantly giving off particles that may or may not exist. And it's giving